reason it's more convenient. So yeah, and Windows, that kind of thing, Apple usually is, when people work in the commercial sector, and that's where they use most of it. um, but for especially for research work and things like that, it's better to use Linux. Apple user yeah, I don't know how to get Linux. It's free, so you just Google Linux and then you download, and then you can install Linux onto your computer. So if you still want to keep Windows like me, you can do a boot. Yeah, I'm using Ubuntu. Ubuntu is the easiest one, that's what I'm using. It's the most user friendly. Yeah, correct. You can do a boot or use VirtualBox. So yeah, Gloria using VirtualBox, and I'm using dual boot. Install in Apple, I think can. Yeah, you can dual boot in Apple, right? In fact, the Apple architecture is built from Linux one, so shouldn't be too difficult. Advantage of Linux well, for one thing, Linux is open source and free, so any software or app you can just download and install for free. So yeah, so if you don't want to do a boot, right, if it's too scary, you can try the VirtualBox first, then yeah, so the fundamental structure, like the underneath the code and things like that, is it inherited from Linux. And if, like, for example, yeah, like if you want to, if you do programming or use LaTeX or things like that, using Linux is better, and it's faster, and it's more secure. Although Windows is, you can be, if you are safe enough in everyday use, is quite secure but Linux is also quite secure. And Arch Linux, yeah, true. So that kind of thing. Okay, so now is 3:03, good time to start. Yeah, correct. So these are the good recommendation for beginners, like Ubuntu and Xubuntu would. So if you want to try out Linux, it's quite interesting and fun, and you can do a lot of things in Linux that Windows cannot. So let's get started with the class. I already started recording, so let's go full screen, right? Full screen. Okay, so this one is a bit weird. Is it because I'm doing it this way? Hang on, some adjustments need to adjust. You can see, right? Make it smaller. Yeah. Yeah, new device, and I'm totally not used to it, so trying to adjust the settings. But today we are continuing to talk about angular momentum. We started already in the end of the previous class, right? So we are just continuing on the story basically. And what we want to do today is basically to continue the story, and maybe at the second half of today's class we will do some tutorial questions that will be you guys are studying now because of the midterm. Okay, so don't forget, our midterm is next Wednesday, so it's soon already, and it will cover chapters 1 to 5, so including the chapter just before angular momentum, which is all about moments of inertia, rotational kinetic energy, and those kinds of things. Okay, so so that is for the midterm, right? And I will upload the solutions for the tutorial and things like that after we finish discussing today. All right, so we're going to talk about some of those questions, and yeah, as usual, I will choose some today. So let's get to it quickly, right? So I will at least try to finish, at least talk about pure rolling, and then we do tutorial questions. So let's continue on with angular momentum. So we have talked about angular momentum last time, right? It's a vector, so as we have commented on it last time, is the original quantity, and then r cross the original quantity, you get the angular quantity. So this p, if you remember, is our linear momentum. So p is equals to mv, right? So this is our angular momentum, and then the direction, use the right hand rule. The magnitude, you use the magnitude of r times magnitude of p sine phi. Phi is the angle between r and p. Okay, so so those things I've shown you already. But right now I want to relate what we did last time for linear momentum. When we learn about linear momentum, right, we see how it is connected to Newton's law, and it is the rate of change of momentum. If there's no external force, then the rate of change of momentum is 0. That's how you get conservation of linear momentum last time. So right now we are going to do it for angular momentum. So let us consider the rate of change. Okay, so rate of change, what is the rate of change? Right, so let's see what happens if I differentiate both sides of the equation. So differentiate a vector, and if you are new to this, right, basically differentiating a vector is like differentiating position to get velocity. We are just differentiating the components by components, but that's a cross product. So how you differentiate a cross product is like this. Okay, so don't worry too much if you're not used to it. I'm just gonna do it once and we'll never use it anymore. This is just to show you something. So the idea is differentiating cross product is like you treat it like a product rule. So it's something times something. So if I differentiate this, I must differentiate the first term and then keep the second one, and then you plus, and then you differentiate the second term. Okay, so this is how you differentiate a cross product between vectors. Okay, so yeah, but don't worry about it. We won't be using that a lot for this course, but next course, electromagnetism, we might need to use more and more vectors. So even though don't worry about it, but at least try to get used to it. Okay, so now let's see what happens to all the terms, right? So this is dr dt, rate of change of position. So this is velocity, and remember what is p? P is just mv. So this is basically v cross mv. Okay, and what happens to this part? This is the rate of change of momentum. We have shown you in chapter 4 that this is just the force. So what we have here is that v cross mv, and m is a scalar number. So scalar number, I can bring it to the front. Is basically just v cross v, right? And then plus the second term is just r cross f. Okay, so let me see if I miss any important messages. Oh, okay, yeah, yeah. Let me finish this first. Okay, so yeah, maybe some of you are not used to this yet, but if you take two parallel vectors and you find a cross product, right, this term is actually 0. Okay, so this term is actually 0, and this term is r cross f. So r cross f is the torque. Okay, so this is the torque. Then what we find here is that this term is 0 plus the torque. So the rate of change of angular momentum is consistent with all the relationship that we carry over from the linear case. Rate of change of angular momentum is the torque. Okay, so that is what we get, right? So and then I think I haven't talked about the dimension of angular momentum yet in the previous class. So let me do this now. So the dimension of the angular momentum is the dimension of L is the dimension of R cross P, right? So what dimension of, so cross product dimension, we don't care whether it's vector or not, we just need to get the units. So the unit of the position is the length, right? Dimension is length, and then momentum is mv, so it's the mass, and then velocity, so velocity is lt minus 1. So we have ml square t minus 1. Correct or not? Correct, right? Yeah, lt minus 1. So the units for angular momentum is SI unit for angular momentum is kg, and then meter square per second. So this is the units for angular momentum, right? So this is what we have been talking about for a single particle, right, moving with respect to the origin, which could be going in circular motion, and is having a momentum p and having a position p r. So r cross p is your angular momentum, right? So this is what we have been discussing for one particle. So now we continue the story to consider many particles. So what is the angular momentum of a system of particles? So let's talk about many particles. And actually what we want to do here is to generalize this to angular momentum of a rigid body. So let us consider many particles going in circular motion, okay, and then with the same angular velocity, right? So if this is the case, we can calculate the total angular momentum, right? So right now what I want to study now is, well, just focus on the magnitude. So let's say I have one particle, right, going in circular motion, right, and then another particle at a maybe different radius going in circular motion, right, and some other particle here going in its own circular motion. So I have many total number of particles. So what is the total angular momentum of the system? It is the summation of the angular momentum of all the particles, okay? So remember, for a single particle going in a circular motion of radius r, okay, what is the angular momentum? It is the mass, the linear momentum times the perpendicular distance from the axis. Am I right? Right? Remember this? We talked about this last time. Okay, so the distance from the axis is r, and then times the linear momentum. Okay, so this is in circular motion because it is 90 degrees with the position vector. So sine 90 is 1. So at the end is sine 90, right? So for a ith particle, I got going at this velocity and going at position ri. Okay, so now all the particle is moving in the same omega, right? So which is to say that the vi will be given by r times omega, and all the particle will have the same value of omega. Okay, they can have different r. So what I can do is I can put this in and see what happens. Right, so if I put this in, and then we have the summation of I, mi, and then omega, right? So I have ri omega ri, and we will recognize something familiar soon. This is mi ri square times omega. So every term has the same factor of omega. I can factorize this out. So we recognize this as the moment of inertia of the system. Okay, mr square is the moment of inertia of one particle in circular motion. So if all the particles added up together, I get the total moment of inertia of the system. So we derive the equation that the angular momentum is I times omega. Okay, so this is similar to linear momentum is mass times velocity. Just that now the linear momentum changed to angular. Moment of inertia is coming from the mass, and angular velocity came from the velocity. Okay, so from here we have seen this generalization many times already, right? This equation will still be true for a rigid body. So a rigid body consists of many infinitesimal particles of mass dm. So which is to say that when I sum up the m of many particles, right, if it's infinitesimal, it is approximately like a Riemann sum. So we do it this way, okay, so that my angular momentum is just the integral of dm r and then omega. So this is how you get I omega, right? So yeah, I think I went too fast. So this is what we did for point particles. All right. Square, yeah, r square, right, and then times omega. Okay, so you change it into this form. Okay, so L is equals to I omega. Okay, yeah, so the reasoning is the same thing, right? We consider many infinitesimal particles, and then we include all the total sum. So for a rigid body, it's just many sum of particles. At the end of the day, this is what we want, right? This is the important point. How we calculate angular momentum. So for a point particle, is r cross p. Okay, no big deal. Okay, but then if it's a rigid body, it's I omega. So there is two ways we can imagine the formula for angular momentum that can come in, and it depends on whether it's a point particle or a rigid body. Okay, so let's see what you guys are talking about. Yeah, you can play games in Linux. You can install free games on Linux, and 2 midterms next Wednesday. yeah, linear algebra, mechanics, calculus, true. Yes, we gave a workshop on this. Yeah, so you can watch this video, and we were using, all these are available on the Linux platform now. So, and you can explore this. You can plot pretty graphs using this. Correct. Yes. V cross V 0 because sine 0. Yes. Correct. So if I take a product, right? Let's say I have a V1, okay, and then another vector V2. So the angle between the two vectors is 0. So the magnitude of V1 cross V2, if they are parallel, then it's just V1 times V2 sine 0. So the whole thing becomes 0. So if two parallel vectors, the cross product will become 0. Okay. Okay. But everything is pretty straightforward so far, right? Nothing special. We are just deriving the same formula that we came from linear momentum, right? Momentum is something like the mass times something like the velocity. So the reason why we want to have this is it will make us easy to use the conservation of angular momentum now. So last time we had conservation of linear momentum. Am I recording? Yes. Yes. Okay, so last time we had the conservation of linear momentum. Now we want to have the conservation of angular momentum. So conservation of angular momentum. Okay. Okay. So conservation of angular momentum happens if there is no external torque. In the same vein where we say when there's no external force, then we have no external torque. When there's no external force, linear momentum is conserved. If there's no external torque, angular momentum is conserved. And the reason is because dl dt is equals to the torque. Okay, so if this is the total momentum of some system, then this will be equals to the external torque. Similar to internal forces, they cancel each other. Internal torque also, we don't need to worry about that. Okay, which is to say that if there's no external torque, then the total momentum of the system, the dl dt, is equals to 0. So what is a quantity that when you differentiate time, it becomes 0? Differentiate time becomes 0 means that it is a constant in time. Okay, so that means during the time from the beginning to the end, whatever this thing is, it will remains the same. Okay, so that is to say how the conservation of angular momentum, right? In the same way that conservation of linear momentum works. Okay, so total momentum of a system will be constant. That is to say, so how to calculating total angular momentum is basically this, right? So total angular momentum is the sum of individual angular momentums, or for plural, momenta of all the objects. Okay, so it will be very clear when we solve an example, which I will do next. Okay, so okay, so but at this stage, does anyone have any question? Okay, so everything clear, right? Should be clear because it's the same, just that instead of linear momentum, everything is angular now. So let us see how it works by an example. So this is 6.4.1, the one with the spinning professor. Okay, so we have a professor stands at a turntable carrying 5 kg of dumbbells in each hand. Dumbbell is this one, for the exercise gym thing. When his arms are extended, his moments of inertia without the dumbbell is this thing. But when he brings his arm close to the body, is this. So this is giving you all the information about the moment of inertia. Okay, so if his initial angular velocity is this much, calculate the final angular velocity. Okay. Yeah, spinning Albert. This is Albert. Who else looks like this besides Albert Einstein, right? With the hair and the thing. Okay, so let us calculate, right? So right now, we are calculating conservation of angular momentum, and in this situation, the moment of inertia change. So the moment of inertia change, we should expect the angular velocity will also change. So let us calculate the moment of inertia before and after he bring his hand in, and then we try to calculate the angular momentum before and after everything happens. So let us calculate the initial angular momentum. Okay, so let's say 1 is the first one. My first angular momentum is the moment of inertia, right? So moment of inertia, the moment of initial moment of inertia should be the moment of inertia of the Albert's body plus the moment of inertia of dumbbells. Okay, so what is the moment of inertia of the body? The question just gave you the number directly. It's just 3.0. And then the dumbbell, we assume it is a point particle because they didn't give the shape and the size of the dumbbell. So if they don't tell you, you can assume it's fair, right? So the dumbbell each has 5 kg. According to the question, each dumbbell is 5 kilogram, and he is holding 1 meter apart from the center of his body. So the moment of inertia of one dumbbell is 5 kg times 1 meter square, right? But he's holding 2 dumbbells, so 2 times all this thing. Okay, so the initial moment of inertia, if you calculate out this number, is 13 kg meter square. And then how about the after? So he is holding the 2 dumbbell and then standing on the turntable, so he's spinning around, right? And then he bring his hand inside. So when he bring his hand inside, the question told you the new moment of inertia of the body, and then we also need to calculate the dumbbell as well in the new position. So the new moment of inertia of the body after he bring his hand in is 2.2. Yeah, 2.2. And then the dumbbell is still 5 kg, but the distance from the center is now 0.2. And I have 2 dumbbells, so 2 times. So if I calculate this number is 2.6 kg meter square. Okay, so using this information, we can calculate the conservation of angular momentum. So conservation of angular momentum, I'm lazy to write the full sentence, it's so long, is saying this. Okay, so the initial angular momentum is I times omega, right? That's the initial angular momentum. So initial angular momentum is equals to final angular momentum. Okay, so it's I2 omega 2, right? So just put in the info given. So initial angular momentum we calculated already is 13, and then omega 1 is given, right? So it's given to be 3.1. So 3.1 radians per second, and then after he bring the hand into the body is 2.6, and then omega 2. So from here we can calculate omega 2, which is 15.7 radians per second. Okay, so yeah. Okay, clear so far? See what you guys are saying? Professor Ong spinning. Yeah, but Professor Ong doesn't have the long hair like Albert. Okay, any question? So the next part is to find the energy, right? So that one is very easy. The initial energy is just half I1 omega 1 square. So we have the information of all that already. So just compute is 64.2 joules, and the second one is you just use the final second values, and it is 321 joules. So if you calculate the difference, right, K2 minus K1, you realize that this is 257 joules. So kinetic energy is not conserved here, it increased during this process. And the reason why it's increased is because there's a change in kinetic energy. So by the work energy theorem, work must be done to bring the dumbbells close. So W is the change in KE is 257 joules. Okay. What does COM stands? Conservation of angular momentum. Yes, I'm lazy to write the wrong thing. So yeah, so K2 is greater than K1, right? The kinetic energy increase. Where does it come from? The reason is work is being done to bring the dumbbell into the bodies. You need to exert a force, and when you exert a force across some kind of displacement that seems to be happening here, the energy increase, right? You can ask, where does the energy come from? Well, it came from the muscles, basically, right? You need some source of energy to bring the dumbbells in, and that is where the energy comes from. So yes, Albert did the work, right? So energy came from Albert's body himself, and this is kind of something that maybe we may have experienced at some point. If you happen to have that kind of spinning table, right, or a spinning chair, even, right? If you hold something heavy and you're spinning on a spinning chair, you try to pull it in. You need to actually exert some strength to really pull it in one. And the reason is here to conserve, the reason is to change angular momentum. You need to exert the force, right? If you have that, you can compare, to really pull it in, you need to exert the force. And also we recognize something, that if we have some mass distributed outside, right, our moment of inertia is larger, right? And if we bring in our masses close to the axis, the moment of inertia is smaller. And if the moment of inertia is smaller, the velocity becomes larger. So this is also the principle that happens when you watch the ice skating, you know. Yeah, mitochondria. It came from the cells. So crying in the toilet. Show the last page. You mean this is this page, or previous page, or last page? When the dumbbell go outside, the energy is lost. Yes, yeah. Is how to get moment of inertia of the dumbbell is mr square, mass of the dumbbell times the distance of the dumbbell from the axis. Yeah. Okay. Any other question? I was gonna say this one is like the ice skating. So ice skating is where the person also spins, right? And then especially the ice skater, they go around and then they jump and then they spin, and then they drop down again, right? And then when they drop down, right, so you notice that when they spin, right, when they drop down, they need to put out the leg. Have you seen the ice skating before? Right? They spin and then they drop down. When they hit the ground, right, you see the person pull out the leg and then they do the pose or whatever but basically they put out the leg with the pose. And partly you see why is that once the person pull up the leg, right, the moment of inertia of that person increases, and that will stop the person from spinning, or at least slow it down. Okay, imagine if you don't pull out your leg, the person spin, she probably do the hand like this, right, and then the leg close to the body, so it just spin, and then we land on the ground, it will still continue spinning like that. Okay, only when you pull out, extend your body, right, with the leg also, then only it will slow the person from spinning, and then you just continue almost at a linear motion. Right? So you know what I'm talking about, right? Yeah, angular momentum of this boy. So this boy has a small angular momentum, right, close to the body. Correct. Yeah. So because you let go, the kinetic energy loss from the system, and then you need to bring it back. You need to put back the energy yourself, contribute the energy yourself using your muscles again. Very low energy loss. Well, you can calculate lah, right? The backwards direction. So from a small moment of inertia, then going to the large moment of inertia, you can use the conservation of angular momentum to find the angular velocity again, and then using that angular velocity, you calculate the kinetic energy. So that is where it's being lost. Okay. Yeah. So it is one of our assignment question, right, about G forces, and astronaut need to withstand very high G forces. Yes, helicopter, which is also another assignment question. Okay, so what time is it now? Yes, let's go to the next example.
Oh, sir, wait.
Yes.
Sir, if we use the angular momentum to calculate that k2 minus k1,
Yes.
and would it equals to mr, or the like when the dumbbell go outside, and will the delta energy be the same?
It should be the same, because just by thinking about it, right, we can calculate but to see, but the change, if you go back the backwards direction, the moments of inertia remains the same. So if you use the
Yes.
angular momentum equation, you get back your omega, the same omega again.
Okay, thank you, sir.
Okay. Yep, thanks. Okay.
Excuse me, sir, but for just now the question, but if you release back, like doing the backward thingy, like just release back your hand,
Yes.
so the energy lost by your muscle like doing the work done to pull the weight to
Yeah.
your body, so
Yeah.
the increase in the there should be the increase in the delta energy, right?
Yes. Yes.
So when your hand release back, the angular velocity should be a bit at least a bit increased, right?
No, decrease.
Since you already do the work done.
It will
I
decrease.
mean, it's like compared to the first time your hand is outside and compared to the second time your hand is outside, the delta omega should be increased a bit, right? Cause you use your body use the energy, I think.
Why Yeah, why? I mean, if you assume ideal case, no friction, and your body convert from your chemical energy to mechanical energy perfectly, it should be the same, right? I think.
Mm.
But of course, yeah, if you say it's not ideal, then yeah, then what you say is true lah. The delta omega might be slightly different.
Oh, so pulling back, I thought pulling back when the mechanical system, like not counting your body energy, the mechanical system, the delta energy will increase.
Uh, you mean pulling back, right? Like what the
Yeah,
question
pulling
says.
back.
Yeah, so the omega increase, so the kinetic energy will increase, and it increased by a lot, by this much.
Yeah, so when you
But if
so the energy from here is not from your body's chemical energy.
it
Or
is
maybe,
it is because you will need to exert a force, right? You
yeah.
need to
So
exert the
when I
force.
release back to the air, when I release back
Yeah.
my hand, so this 257 joules is not disappear, right? It's not back to like.
Yeah. So good question,
So
because
the second time you pull is another 257 joule, right?
correct,
So
correct,
that like every single time you pull is another extra two five
correct,
seven.
correct.
So the delta energy will keep increasing, right? Like
If
for the
I
moving
mean,
system.
if you say you add up from all the previous ones, then yeah lah. Correct, correct. So I think, yeah, we are saying the same thing. You're just adding up from the previous times, right? So yeah, 200 each time, 257. You let go,
So
and then you pull yourself back again, still 257, right? Let go again, and then you pull yourself back again, still 257.
But when I let go the 257 from the first time, what disappear, right? It still got back to the kinetic system, is it?
So if you let go, right, you slow down, your kinetic energy decrease.
But where's the energy goes then? Like this 257, one goes disappear.
You can say it goes to the loss to the environment, or it is a negative work done lah. So it is a negative work done. So it's being done by the centripetal force basically. The rotating system, yeah, just
Or done by the centripetal.
Yeah.
Huh? Okay, then maybe yeah. I think I understand. Thank you very much.
Okay. Yeah, that's a good question, because we like really think carefully where does the energy goes to. So if you just let go, right, then the centripetal force is the one that will push your hand outwards, right? You just relax your body, it will swing outwards because of the centripetal force, and that is where the work is being done. Yeah. Okay. Yeah. So that's an interesting way to.
So the work Albert done, so is it just to increase the kinetic energy, or also can be used to change the moment of inertia?
Both. So they are
Oh,
connected. Yeah. Because the work he's done is to pull himself in. It changed the moment of inertia, and that is at the same time, that is the reason why changing moment inertia increases the kinetic energy, because of this calculation.
and will energy be used to change the moment of inertia, or we can just say, well, the energy is changing and also the system is changing, so they like changing in a parallel line, just
No, actually they are connected. The reason why they are changing is connected. So definitely there is work being done, right? So
yes.
right, so work is being done. So you need to. That means is tied together. That means in order to change the moment of inertia, you need to exert some force, and the reason is because he's spinning. So there's the spinning object has a natural tendency to spread out. You are going against the natural tendency. So you need to push it in. That is the work being done to change your moment inertia.
So that's the positive work being done.
Yes.
And it's just I'm not I don't know if we just change the moment of inertia, will we do works on this part?
Um, it depends on the angular velocity. So if the angular velocity is 0, right, then
Yes.
you can just change your mass distribution. You can just push it as if you push it
Yes.
at, yeah, right, is zero velocity,
Oh,
constant
yes.
velocity, then so it
Yes.
depends on the
Okay. Thank
omega.
you, sir.
Yeah.
Sir, can it be said that the work is done to change the magnitude of centripetal force when you pull it in? Because you're
Well,
pulling it in, so can it be said that the force is used to as centripetal force?
well, your force is, yes, the force that you exert is working against the centripetal force. That is why.
So conversely, when you let it go back again, then the force goes to the centrifugal. Then the work done goes to the centrifugal force, right?
Correct.
The thing flying out.
Correct. Yeah.
Oh, okay. Thank you, sir.
Okay.
So I have another question. So when I push my hand out, like when I'm turning, the centripetal force will like pull my hand out, right?
Yeah. So
But
you
what
don't
if
need to push. You just let go. You just relax your body.
yeah,
It will fly out.
what if I use my force to push my hand out, so the energy, the system will increase their energy? Hell yeah.
I think it makes no difference, because you're just helping the centripetal force in this case. So if you push your hand out, right, that means the centripetal force, oh, someone do my work for me, so the centripetal force can relax a bit, right? So that means but the net work done is the same.
Huh? Still the same,
Yeah.
Okay then.
Yeah. Because the net result is, you're just helping other people do the work for them. You're just helping centripetal force to do its work. So
Then where the centripetal force go? Like I helped him to do his work, then you don't need
It's
to.
like if you put a book on the ground and you lift it up, but not up in the air, just like that, or
Yeah, something like that. Right, so if you put a book on the ground, right, the normal force will cancel the weight, right? So that the book
yes,
will remain. But if you just try to
yes.
lift up a bit, then the normal force will decrease. But if you don't lift up all the way, the normal force will just need to do less work, less force. That's the reason.
So
Um,
net force is always the same, and
Yeah, but right now, yeah, but for correct. In that example, correct, if it remains in equilibrium. But of course, here we are going too deep already. We did not consider what is the force. If we did not consider when the hand go out, what is the velocity that it goes out, whether it's accelerating out and then stop. So that one will affect all the details, right? So,
oh yes.
right, yeah. So then we
Okay,
really
thank you,
need to
sir.
calculate. Okay. So before we run out of time, we really need to continue this next example. Is this one. This one, yeah, so this one, I don't know if it's harder or easier compared to what we just discussed, but it goes like this. We have a door and then can rotate freely about the axis, and then we have a bullet that you shoot, right? So initially you have a bullet and then it stuck into the door. Once it hit and stuck into the door, the whole thing will rotate together. So we just need to find the angular speed. I should add the word just after collision, okay, because it will not remain the same. But let us calculate this situation, okay. So let me do it in a way that is more clear than the original question. So if you read the info given, the bullet is shooting at a distance of 0.5 meters away from the hinge, but the door itself is 1 meter long, so it's like halfway through. Okay, so the mass of the door is 15 kg. The mass of the bullet, we call it little m, is 0.01 kg, and the initial speed of the bullet is 400 meters per second. Okay, so the bullet shoot on the door, and then once it hit and gets stuck on the door, so it's stuck already, and then it is a pivot over here, so it will start to rotate, and we just need to find what is the angular momentum right after it got stuck on the door. Okay, so this is what happens before collision. This is what happens just after collision, right? So let us try to calculate. Because there is no external torque, right? No friction on the hinge and nothing, then angular momentum should be conserved. So let us calculate the angular momentum before collision. Okay, so before collision, what is the total angular momentum of the system? The door is not moving, so 0 there. Only got the bullet, and the bullet is having a distance of this perpendicular distance from the axis. So the angular momentum is mvl. Remember, right? When we talk about angular momentum of a straight moving particle, perpendicular distance from axis is mvl. Okay, so we can actually calculate this number out. Initially it's 400 and then 0.5. So if you put out the numbers, you get 2, right, kg meter per second. Now, what is the angular momentum after collision? So after collision, right, it is no longer a straight moving object, it's just a rotating body. If it's just a rotating body, then you just need to calculate the moment of inertia of the system times the omega. What is the moment of inertia of the system? Well, moment of inertia of the door plus moment of inertia of the bullet times omega, right? And by conservation of angular momentum, these two should be equal. That will help us determine omega. So how we determine omega? Moment of inertia of a door. This is a uniform straight rod kind of thing, and we have spent so much time calculating already, right? Hopefully we remember it's 1/3 ml square. The bullet is a point mass, so it's m, the distance square, so it's 0.5 square times omega. Okay, so so we can easily calculate this. The mass of the door is 15. The length of the door is just 1. Mass of the bullet is 0.01. The distance is 0.5 square. That gives me omega. So the number is 5.0025 omega. right? So the 0.0025 came from the bullet, so it's actually quite negligible compared to the door. But if we say conservation of angular momentum, right? So conservation of angular momentum, again, I'm lazy to write the whole thing. No external torque means this is true, right? So 2.00 is equal to 5.0025 omega. So omega is 0.4 radians per second. Okay. So is that clear?
Sir,
Yes.
can we calculate the energy when the bullet is stuck in the door, and then we can know that the angular velocity?
No, because remember, right, this is the same as the linear momentum. Linear momentum, there's elastic collision and inelastic collision. So only for elastic collision, we can use the energy.
Yes, but I mean when the bullet is stuck in, I mean after or started from the bullet is stuck in the door, and is it energy conserved?
No, it's not conserved. In fact, the question asks us to calculate, right?
Yes.
Yeah, so KE, we can calculate kinetic energy before collision. We can actually check the number is half mu square. So if you put in the numbers, you get 800 joules. KE after collision is moment of inertia door plus moment of inertia bullet omega square, right? It becomes a rotating system, so it becomes omega square. So if you put in, we have calculated just now already. So if you put in the numbers, it 0.400. So you can see the kinetic energy is not conserved. So we cannot use kinetic energy to calculate.
Okay, thank you, sir.
Okay. Yeah. Any other question? Wow. 3:48 already. Okay, so if you can bear with me, right? Let me start talking about rolling motion at least very quickly. And rolling motion is the whole reason why I'm in Windows right now, right? Because I want to show you some animations. So let us talk about rolling motion. Okay, so let's go to 6.5, rolling motion. Okay, so rolling motion is about object rolling, right? And it is a chapter that I think a lot of people will find it very challenging, and it's because we are now mixing up the two types of motion all at once. Because remember, right, when we talk about chapter 1 to 4, all about linear motion, just we ignore the shape of the object, we just look at the center of mass and then just see the linear velocity, linear momentum, linear force. Okay, and then in the past 3-4 lessons, we start to talk about rotating bodies, right? So we don't care about the translational motion, we just see how it rotates about the axis. But a lot of the things, they do both at the same time, right? They will rotate and it also move, like a bicycle wheel, right? A bicycle wheel is rotating about the axis at the center of the wheel, but the whole bicycle is moving. So it has two types of motion at the same time. So now we want to learn how to figure out this type of motion. So this is a motion of a rolling body, and it consists of two types of motion. So firstly is the translational motion of the center of mass, and then we talk about the rotational motion around the axis. Okay, so we have been studying these two things separately, but now we want to consider them both at the same time. Okay, so that is where the tricky part starts to come in. Okay, so in chapters 1 to 4, we have learned how to solve this part already, right? So we use Newton's laws, right? So we say F is equals to mass times acceleration. Once you get the acceleration from the acceleration we can get the velocity, we can get the position, and whatever quantity, momentum, right? That kind of thing. Okay, so so these are the, like, this is the motion of the center of mass. Okay, so in particular, right, one important quantity that I want to is two, not, cannot, is my pen can see, you can see my writing, right? So this is the motion of the center of mass. Okay, so and then the important quantity that I want to talk about here is the velocity of the center of mass. Okay, so that is by solving the translational motion. So we have done this since chapters 1, 2, 3, and 4. Okay, in chapter 5 and 6, we've been doing now is about rotation, right? And we use the torque to solve this, right? So the rotational Newton's law, so the torque is equals to I alpha, right? So the I alpha, if you know the torque acting on the system, we can calculate the alpha. Alpha is the angular acceleration. So this is the angular acceleration of the rotation. So once you calculate the angular acceleration, we can calculate the omega with theta and or whatever kind of things, right? So and then, right, from the from the omega especially, right, we also calculate the tangential speed of the object. So the tangential speed is given by the radius times omega. So this is the tangential speed at the edge of object. Okay, so this is the velocity of center of mass. Okay, so what I want to emphasize now here is that we will consider, so there's two important quantities, and I think most of the mistake come in when we confuse and mix up these two velocities. So there's two velocities happening at the same time. Okay, but actually it's very simple. If we talk about center of mass, we use Newton's law to solve it, then done, right? We know how to do it since chapter 1. Then if we talk about V tangential, we use all these torque things. We've been doing this since chapter 5 and 6, also done, right? So as long as you don't, you just know which is which and you don't mix up these two, then it should be quite straightforward to solve. Okay, so this is the situation that we have over here. Show, wait, show previous page. I didn't see. Is it here? Or was it a long time ago, the message? I don't remember. Wei Zheng, my visualizer. Oh, okay, sorry. Yeah, it's been too long since I checked message. Will we do vibration? Will we do vibration? Yes. Chapter 7. 7 and 8 is harmonic oscillation. 8 and 9, harmonic oscillation and wave motion. Okay, so we will do that. Okay, so to see what is happening here, right? Yeah, so what we will typically solve is like a wheel rolling on the ground. Okay, so if a wheel rolling on the ground, right, usually the center of mass is right in the middle. So this is the velocity of the center of mass. And then if you pick any point, right, let's say I choose this one point. So this will go in the having a tangential speed. But you see, right, this is where it's becoming tricky. Velocity is a vector. So you see the direction is here. The direction of this is always here. But for the tangential part, right, it will depend on where it is. So it will be here, it will be here, that kind of thing. Okay, so drawing to show you is very difficult, which is why brand new things, yeah, which is why I come to Windows, because I want to show you the animation. Okay, so over here, actually they got animation related to earlier chapters, but I didn't show, no time, and I forgot. So as you can see, right, let me show this, make sure it appears on the, okay. So as you can see, right, this is a rolling motion, and we imagine the camera is following this wheel rolling on the ground. So this wheel is going forward, okay? and we follow the motion of one point going around. So at the moment we are considering pure rolling. I will explain this in a more detail later, but right now there's two types of velocity. So let me pause the picture. Okay, and this horizontal blue vector here is the velocity of the center of mass. So this whole thing is going to the right at some velocity. So it's in arbitrary units 603. And then if the tangential part, right, the tangential is always tangent to the circle, so it's in this direction, and the tangential speed in this case is the same magnitude as this. So from these two vectors you can calculate the total resultant vector of this point. So the resultant vector is the sum of these two vectors, so you got these two, right? So as it goes along, right, you see that the center of mass is always pointing to the right horizontally, and this one is always tangential, okay? And therefore the resultant vector will always change depending on its position, okay? So clear, right? So this is our situation that we have right now. And so this is rolling motion. What time is it? Yes, I use GameMaker to do this. Yeah. Okay. But yeah, it's 4 o'clock, right? Okay, so let me I'll tell you what. Let me just finish this bit first, and then we continue with the tutorial. Okay, so I will just briefly comment that there is 2 types of motion. Okay, so we have, firstly we have full screen, pure rolling. So pure rolling is where V tangential is equal to V center of mass, and rolling with slipping is when they are not equal. Okay, so I'm talking about the speed, right? The magnitude are the same. These two are not the same. So these are 2 types of motion. And without explaining the technical stuff in detail, right? So I will leave that next week. But let's see what happens if I change the velocity of one of them. Okay, so see if the V tangential is faster than the V of center of mass, right? Then the 2 magnitudes are not the same. So the reason why it's slipping is because these 2 vectors are not the same, so there is a net velocity here. So it's scraping against the ground. Okay, so this is rolling with slipping. Okay, so only when they have the same magnitude, then it becomes pure rolling. Okay, so yeah, so so I think now is a good time to take a break. So let us rest for about 5 minutes, and when we come back we will do some tutorial questions. So yeah, sorry I took too long. Yeah, so the animation was made using GameMaker. I can upload the exe file on Moodle if you want to play with it. Is it spinning faster than it's rolling? Correct. Actually, both cases. If it's spinning faster than rolling, or also spinning slower than rolling, it will also slip. Right? So I can actually do it the other way. So this one, the tangential is faster, right? So V tangential is higher than VCM, but if it's slower, also it will still slip, but it just slip the other way. Yeah. So anyway, yeah, you guys can take a rest, and we will come back in about 5 minutes time. Okay. Yes, 2-way. I mean, yeah, in a way, it's a 2-way slip. So because there's 2 possibilities. Rolling with slipping happens when these 2 are not the same, and they are, of course, when they are not the same, right? V tangential can be higher, or V tangential can be smaller. There's 2 possibilities. So yeah, so these are the 2 possibilities. Okay. Actually, there's a projectile motion you can play around with here also. This one is quite fun. It's almost like a game. You can shoot things, but you can, this is where you can show the direction of the vector. Wait, how to show that? Yeah, so you can see the direction of the vectors. Okay, I didn't show because it seems like everyone is quite okay with projectile motion, so no need animations to show, or no need to play this stuff. But if you want to play this, I will upload it on the Moodle. Okay. By the way, since we're in a break, let me stop recording to save space. Okay. When the car one side of your tire touch the water, your car will turn the side. Yes. So the reason is because water reduces friction, and we control the motion of our car using friction. So if one side of the car touch the water, right, it will turn. Yes, because the friction will reduce, the water on one side will reduce the friction, so on one side will have a smaller force, so your force is not balanced anymore. So when your force is not balanced anymore, right, so there's going to be some net force on one side of the car, so your car will make it turn. Yeah, so it's sliding on one side, so it will turn. But of course, to really solve this, it will be a bit more complicated. You need to know what is the force here, and then whether the car is constant speed or not. If it's constant speed, and then the water on one side will reduce the friction, so this will make it, I think it will go front, right? Because the static friction will actually sustaining the motion of the car. So I think it will make it go forward a bit. So yeah, so the main reason is it will reduce the friction. And I say reduce the friction, that I'm implying is sliding, correct? Yeah, so the tire is sliding. So yeah, so these are all the complicated details that if you want to solve it in a question is actually very complicated, so it probably won't come out. We probably don't need to worry about it, but the idea is, the concept is this. Yes, so the coefficient of friction between water and rubber is very small, so that means the static friction is very hard to maintain with water. So when you come across water, it will easily turn into kinetic friction, and that's why it's sliding. And even if it's kinetic friction, the force is still small, so it will also, yeah, the net force will also be reduced, and that's why when the tire is sliding, and once the tire slide, it's very hard to control the motion of your car anymore. So that is why. Okay, so let us solve a tutorial question. Let me start with question 2. I know question 2 is considered easy, but I want to do this to remind everyone that when it comes to elastic collision, right, there's a formula that students always forget to use, and students end up using the more complicated formula. So let me show you this question. So we are at tutorial 4, question 2. Okay. So we have an elastic collision between a neutron of mass m. So let's call the first object m1 to be neutron, right? And then original speed to be u, so u1 is non-zero, it's some u number, and then it's colliding with a neutron, deuteron, which is, I will call this object m2, and it is twice the mass of the neutron. Okay, and the initial deuteron velocity is 0. Okay, and it's initial at rest. So what is the speed expressed after the collision? And then find the kinetic energy as well. So again, right, when the question didn't say anything about the direction, it is fair to assume it's a linear motion, because if it's direction, then they didn't give information about direction, so we can't do anything, right? So let us solve this question. We just want to find the velocity after the collision, right? And we want to find v1 actually, but we don't know v1 and we don't know v2. But this is an elastic collision. Okay, so when it comes to elastic collision, right, the kinetic energy is wait, what happened to my full screen? When it comes to elastic collision, right, the kinetic energy is conserved. Okay, and of course it is a collision, so momentum is also conserved. So therefore you have two things that are conserved. And if you recall what we did in our lecture, when it comes to elastic collision, we derive a formula that is quite useful for this case. Okay, so let me quickly fix this and then we continue. Okay, full screen. Okay, so when it comes to elastic collision, right, we derive a formula. So you can just use this formula straight away. Remember how we got this formula? We consider conservation of kinetic energy, conservation of momentum, and then we manipulate the two equations, we cancel some terms, we arrive at this stage, u2 plus v2. So when it comes to elastic collision, we can use this equation, right? So the question is asking what is v1? We don't really care what is v2, so we will eliminate v2 away from the equation later. So I got u1 minus u2 plus v1. Okay, so I have this first equation now. Okay, I have two unknowns, so I need a second equation. So to get a second equation, we look at the conservation of angular momentum, a linear momentum, right? Which is to say that m1u1 plus m2u2 is equal to m1v1 plus m2v2. Okay. Am I recording? Yes. Okay. Then we plug in the values that we know so far. So from what we know so far, m1 is just some number, m0, and then this is some initial velocity. m2 is initially at rest, so this whole thing becomes 0. m1 is still v0, v1 is unknown. m2 is twice of m1, so it's 2m0. And then v2 is another unknown, but I have calculated an expression for v2 here, so I can put my v2 inside. Right, so I got m0u1 is equals to m0v1 plus 2m0 u1 minus u2 plus v. Okay, now at this stage it's very easy because every term has a m0, so I can cancel this away. So u1 is v1, and then I got u1 minus u2, 2u1, 2u2 plus 2v1. Right, so this term I can bring over there, it just becomes let's keep it here first, right? So I have v1 plus 2v1, so I got 3v1, right? And then I got plus 2u1 and then plus 2u2, but actually I forgot, right? u2 was already 0, so no need to keep it there, right? And then I bring this term over here, so I got 3v1 is equals to negative u1, so v1 is negative 1/3 of u1. Okay, so the speed is just taking the magnitude, so it's just the 1/3 of the original speed. Okay, so that is the velocity after collision. Okay, then so once we have found the final speed, we compare the kinetic energy. So we want to find the neutron initial kinetic energy, okay, is equal to half of the mass and then u1 square, and then the neutron after collision, so the final kinetic energy is the same mass, but now it's going at 1/3 the original speed, right? So what we found is that is 1/3 square is 1/9 times 2 is 1/18 m0 u1. Okay. Oh, one none. Okay, yeah, no problem. But you're back, okay, okay. Yeah, welcome back. So if you miss any, yeah, nothing much. We are still solving this question. Okay, then we need to find the ratio between the original, right? So ratio is equals to the final kinetic energy divided by the initial kinetic energy is just 1/9. Okay, so this part is very easy, right? What the reason what I want to show you this question is that it's faster to start with this equation, right? No need to use half m1 v1 squared, half m2 v2 squared equals to half mu1 v1 squared. That one is more messy, right? Actually, it's consistent with the same equation here. Okay. Any question? Okay. Everyone fine, huh? So let's do question 8. Okay, so the rest are like I feel is straightforward. I will put the solution, don't worry. But I do the question when I see things I want to emphasize. So I think this part, questions like question 8, I think some people are still not very confident in solving. So I want to show you question 8 in detail. So we have a small wooden block in 8 kilograms suspended from a lower end of a light cord that is 1.6 meter long. So yeah, so I have a cord of 1.6 meters long. Okay, so let's call it L. So L is 1.6, and the block is initially at rest. Okay, so the block is initially at rest, and then a bullet with a mass of 12 grams is fired with a block with horizontal velocity v0. So the bullet strikes the block and becomes embedded. After collision, it will swing together, right? And then vertical height. So we determine what is the initial speed. So so let us calculate this problem. So let me show you how to solve. Okay, so I have a bullet. It will strikes right after it got embedded. It will swing together as a combined object, right? So it will swing with the bullet inside, and according to the question, it goes up by amount of 8 meters, right? So the change of height is 8 meters. Okay, and to make it easier to solve, right, let us look at the angle. So this angle is theta, right? So this angle is theta. The length of this is 1.60 meters, and so this part should be equals to L minus this part. So this part is L. So this is equals to L minus L cos theta, right? So the change in height is 1 minus cos theta. Am I right? Okay, so we can actually calculate this. Then h over L, we can see that this is 1 minus cos theta, and h, according to the question, is 0.8. This is 1.6. So this is actually half. Okay, so h over L is equals to half. And then the information given to us is also the mass of the bullet is given to be 0.012 kg. The mass of the block is, I call it M2, is 0.8 kg. So the total mass is M1 plus M2 is equals to 0.812 kg. Okay, so based on this information, right, how do we get the initial speed of the bullet before collision? Okay, so so we do it this way. So let's say, right, after collision, it becomes v0. So initially, the bullet fly has some initial speed u, and then it get embedded to the block. So get embedded to the block, we use, this is an inelastic collision. If you conserve angular momentum, after where it becomes v0, right? So this v0 is having some initial kinetic energy. Using this kinetic energy, you will use it to climb up this potential height. Okay, so okay, and then we also given that the tension on the string is where's the question, is 4.8 newtons, right? Any question? Anyone asking question here? For question 2, Ka Heng was asking this. Where this came from is when we were doing chapter 4. Yeah. But let me continue this question first. I will come back to this later. Okay. So how do we solve this question? Well, it gave us the tension, right? So the speed, we do not assume anything about the speed. The question didn't say it's at rest. they do give us the tension here. So we can treat this as a circular motion, and we can actually calculate the speed here, right? So if we can calculate the speed here, then we can determine the energy when it's here. Once we determine energy here, we can find the energy here, and then we can get everything else beforehand. Okay, so let us draw the free body diagram. Let's call this position 2 and position 1. Okay, so position 2. Okay, so the free body diagram at position 2 is this. So my object is attached to a string, and it's going at circular motion of radius L. They told us the tension T, which is 4.8 newtons, and as usual there's a weight. Okay, so the angle theta we have considered previously was this, so we can resolve our mg this way is just same theta, right? So it's mg cos theta. Okay, so from here we can get the centripetal force. What is the centripetal force? It is T minus mg cos theta. This is the centripetal force, so it should be the mass times acceleration. And since this is a circular motion, the acceleration is radial, is mv squared over the radius, so it's mv squared over L. Okay, so we got this now. Then we can actually calculate the rest of the quantity. Sorry, this should be big M, right? This is the total mass of the system. So everyone clear so far? Right, so the V square we can actually find is L over big M, T minus this is big mg cos theta. Okay, so we can actually find cos theta. 1 minus cos theta is half, so cos theta is still half, right? So it's 60 degrees. Then we can actually calculate the value. So the length of the string is 0.6. The mass of the total system is 0.812. The tension is given to be 4.8. And then 0.812 again, 9.8, and half. So this will give me the speed of 1.272 meters per second. Okay, so now that we got this right, I have found the speed here. Okay, so I found the speed here, so I can use conservation of energy. Okay, so the energy at position 2, position 1 is equal to energy at position 2. So position 1 is when I'm down here with the bullet, right? Going at velocity v0 just after collision. And the energy at position 2 was what we just calculated over here. Okay, so we can actually consider this. So the energy at position 1 is just purely a kinetic energy. So I got half total mass, this v square, and then position 2 it has risen up by mgh, and then plus half I omega square. Okay, so now we can well, we can just put in the information that we know, right? So using this, right, and then mgh, this is well, this is half, and then this I, what is the moment of inertia of this system? This is just a pendulum. The string, we ignore the mass, right? So it's just a point mass at the distance L from the center. So it's just the total mass times distance square from the center. So I got this thing omega square. Okay, so so all these values of the numbers we know already. We should be able to calculate the speed is going to be 281 meters per second. Okay, so once we calculate the speed, this is the speed just after collision. Okay, then how about before? We use the conservation of momentum. So before is the bullet haven't hit the box yet, and then after hit is going at v0, so this is u. Okay, so we can calculate this. So this one is at rest, so the initial momentum is just m1u, and then after it colliding it becomes m1 plus m2 v0. So from here you can calculate the v, the initial velocity. Okay, so yeah, any question? Okay, yeah, so the yeah, so where to get the momentum equation is at the beginning, right? I remember some kinetic elastic collision. See, starting from if it's an elastic collision, I can use linear momentum and I use kinetic energy, and then I manipulate these two until I get this I get this relation. Okay. Why have 0.5 I omega square? Where? Where was it? Zero 0.5. Oh, sorry, I think I went too fast. Okay, basically, yeah, because there's too many numbers in the story. So let me tell the story again, but we don't care about the details. Okay, so so what's happening here, right, is I have u. Okay, so then this one is before collision. So the question is asking us to find what is u. Okay, so this is before collision, and then after the thing hit the box, right, so the bullet is inside. This is just after collision, right? So just after collision, it will embed together and go at a speed v0, and then after the collision, right, the question continues some more. It will swing upwards until here. So this is position 2. So this is v, right? So this it swing from up here. So the height of the swing is 0.8. Okay, so this is cosine theta, right? So this object is having mass m1, this object having mass m2. So after collision, the total mass is m1 plus m2, right? Same thing, so the total mass here is m1 plus m2. Okay, so do you follow so far? Okay, so what is happening here is that the momentum here, the momentum is conserved here, right? So the momentum is conserved here, so it's m1u. So the initial momentum is just m1u is equals to m1 plus m2 v0, right? And then from here to here, right, this is swinging upwards. There's gravity, so we do not count momentum anymore, but we still consider energy. So here energy is conserved. Maybe I should have started like this, so it's easier to, I kind of like this way to describe now. So after so at this point, right, it's having the initial kinetic energy. So it's half m1 plus m2 v0 square is equals to the energy here, so it becomes m1 plus m2 gh plus like this, so it's half I omega square. Also, you're asking this, right? So this is object of mass m1 plus m2 at a distance of L from the axis. So the moment of inertia is m1 plus m2 L square. So does that answer your question if I say it like this? Yeah. Yeah, okay, good. Why not half mu square, half mv square plus half mgh? Because this is an non-elastic collision. It didn't say it's an elastic collision. So kinetic energy is not conserved. Okay, so from here to here, Ke not conserved. From this step to this step. Okay, yeah, there's energy loss. Yeah. Yes, after the bullet start, yes. So this is what we do here. So actually Ke not conserved, that's potential energy. Yeah, we can do it here. That's why here. Yeah, so this part is momentum. So momentum is conserved from here to here. Here, nothing to do with momentum anymore. But energy, right? Ke not conserved from here to here, but here total energy, yes, from Ke to potential plus rotation. Yeah, use potential and Ke, yes. Okay. What time is it now? How to get, wait, V squared over 2L. Huh? But you use in high school, are you sure? Cannot do it this way in, yeah, whether high school or not is wrong, right? Because Ke not conserved. Because there's an inelastic collision here. So energy loss when the bullet gets stuck in the block. Yeah. This equation, yes, but not this U, right? This V, yes, not this U. How to get V squared over 2L? I mean, so then you can say over here you can draw the free body diagram, right? So just now we got T minus mg cos theta is equals to m times a, right? And this is a circular motion. So circular motion is V squared over the radius. So yeah, nothing special about it. So a is V squared over 2L. If oh yeah, so just now, that was earlier, right? Yeah, if V not square, yes, then it's okay, because what you're saying is this part. Wei Zheng is saying is this part, this equation, yes. What else? Oh, okay. So yeah, I think the remaining question is Charles' question is V squared over L is the radial acceleration. So from chapter 1. Yeah, too much letters. Okay. Yeah. So how are you guys with the other question? Because since we had quite some discussion, right? So I didn't expect to run out of time. Because looking at the time I have left, I can either do some of the other questions, but if I'm uploading the solutions, maybe you don't need me to solve it in front of you guys. Maybe you want me to do this one, I'm guessing, right? So shall we do this question? We will probably spend 10 minutes, just enough time, and that will be, yeah, so it's just within time to do this one question rather than to do 2 or 3 more other tutorial questions. How's that? This looks fun. Okay, so how do you find the center of mass of a curved object, right? So this is another tricky question. Okay, so let's see. So what we have is, this is question 15, right? Question 15, and what we have here is basically, let me draw the axis first. So this is the origin, right? And then we have a circular shape rod thing from here to here. Very ugly. Let me try again. So I got this, right? And then from here to here, and then I have a circular shape thing. Still very ugly, but yeah, no choice. Okay, so the total length is L. So this is my y-axis and this is my x-axis. Okay, so this is some unknown radius. Let's call it A. We can actually express A in terms of the angles because this angle is 90 degrees. That piece of paper. I mean, yeah, I can still use it for do other things. Looks fun but feel bad while doing. So how do we find the center of mass of this this object? So this is a uniform rod, right? So uniform rod. But firstly, it will be convenient to know what is the value of A. So the first of all, right, well, we know the length is just given as L, so it's some standard fixed quantity. So it's some given quantity, and from here we can say that the length is the radius and then times the angle in radians. Okay, so the radius is A and then the angle in radians will be pi over 2. So from here we got A is equal to 2L over pi. So we got a formula for A now, right? And then we want to, yeah, so 2 pi A is equals to 4L. Yeah, so yeah, basically the same as this equation, right? After you cancel out the 2. Now, the next thing to do is we do our usual thing, right? So we consider in an infinitesimal mass and then we try to sum up the total thing. So let's look at one infinitesimal mass, right? So let's take one section of mass dm. It is very short, so it has some short length is equals to ds, right? And this short length is, well, everybody has a fixed radius a from the center, right? This short length from here is equals to, well, is some radius, because length is radius times angle, so a short length will be given by radius times a little angle, tiny angle. Okay, so we got that. Then another thing is we use the information that it is a uniform rod. So if it's a uniform rod, then the mass per length is, I call it lambda, and it's a constant, right? We've been doing it so many times. Okay, so my dm is equals to lambda ds, and then my ds is given by this, right? So we say that dm is equals to lambda the radius times the theta. So let's try to get our total mass. So the total mass is the integral of all the dm, right? So all the dm will be lambda a d theta, like this. And then to get the total mass, I'm integrating all the points, right? So let's start with the first point. So the first point is 45 degrees, right? So then the final point is 270 degrees, right? So 3 pi over 4. So my integration limit is from pi over 4 to 3 pi over 4. Basically it's pi over 2 again, so it's lambda a times pi over 2. So from here we got the formula for lambda, right? So the formula for lambda is just bring this down, so I got m over a pi over 2. So lambda is 2m over pi a. Okay, so then we got the formula, because just now dm is given by lambda a d theta, so we got the formula for lambda now, which is over here. So my dm is equals to 2m over pi a d theta. So cancelling this, right? So my dm is equals to 2m over pi d theta. So everyone follow so far? Yeah, correct, huh? So I got my formula for dm now. So now let's try to find the center of mass. Okay, so my center of mass is this. So to get the center of mass, I need to get what is my xy coordinates of my center of mass. So my xy coordinate of center of mass is using the formula, right? Is the 1 over m times the integral of x dm, and the y coordinate is equals to 1 over m y dm. Okay, now since we're a bit short of time, right, I will just calculate this. Okay, but hopefully it should be clear enough that because this is right at the center, okay, and it's symmetrical at the center, so the x coordinate of the center of mass will be 0. Okay, I don't have time to show you the calculation, but hopefully you see why, right? It's by symmetry. It's a uniform rod, so it should be somewhere at the center. Okay, so we have found this. So now let's try to determine the x coordinate. So my position of the center of mass is somewhere on this axis, because left and right are perfectly spread out the same. So it should be somewhere on this middle line, but where exactly? What is the y coordinate? So this one we really need to calculate. Okay, so we need to find what is my center of mass of y. Okay, so I need to get y cm is equals to 1 over the m, and then my y coordinate, and then dm. Okay, so how do we do this? Well, first of all, what is my y coordinate? So if I take any infinitesimal point, right, the radius is r. So, and then if I take my angle with my horizontal axis, this is like the Cartesian coordinate vector. Y coordinate is a sine theta, right? If I take any point, dm, right? So the radius is a, so it's theta. So what is my y coordinate? Right, so y coordinate is a sine theta. Do you agree? Okay, right? So y coordinate is a sine theta. So I'm going to put this in here. And then just now we have already found my dm. So my dm is over here. So dm, I can put it into here. Okay, so my y coordinate cm is equals to 1 over m integral of, well, let's see what we have. We have a sine theta, and then dm is 2m over pi d theta. Do you agree? Okay. Okay, so seems okay, right? Yeah. Okay, so if everyone agree until here, right, then the rest is easy already. Too geometrical, is it? Yeah. This is my best, to me is the easiest way to understand but there's many different ways to derive. But if you agree until here, right, then the rest is just continue finishing this, then you got the almost done already. Okay, so once you got to this stage, you need to decide your integration limits carefully. Okay, so my theta is the angle within the x-axis, so I should start from my starting point should be what, and my ending point should be what. If this is 90 degrees, right, then my starting point should be pi over 4, like just now, from pi over 4 to 3 pi over 4. That's how we get the total mass. Okay, so it's just 2a over pi. Integrate this, will give you cos theta from pi over 4 to 3 pi over 4. Okay, then you just calculate this. So this is square root 2 over 2, square root 2 over 2, so you get square root 2, right? So you got 2a over pi, and then you got positive square root. So my y position of my center of mass is 2a root 2 over pi. But just now we have expressed a in terms of L, so a was 2L over pi. So we put this in as well. So my YCM is 4 root 2 over pi square L. Right? Okay. Any questions so far? Right, so this is almost done, but this not the question is asking for, right? The question is asking for the distance from the center. So what we have found is the YCM coordinate, right? So my YCM coordinate is given by this. The question is asking for, yeah, this number is really tricky. That's true. The question is asking for D. right? So to get D, or not easily visible from the graph. You mean my drawing too ugly, or it's not easy to see from the diagrams? D. Meanwhile, let me finish this first. We're almost done. Because the radius is A, right? So the distance here is A. So the D is equal to A minus YCM. Okay? So, which is to say that it's A minus 4 root 2 over pi square L. So the A is what? So the A is 2L over pi, right? So it's 2L over pi minus 4 root 2 over pi L. So in other words, this is 2 over pi minus 4 root 2 over, sorry, pi square, and then L. So this is the distance. And if you want to check the numerical value, is about 0.0635 L. Okay, so it's about some portion of the length away from the center. Okay. Yeah. So just fill in time. Any question? Any other question? Was that clear? Okay. So yeah, so don't be scared if you find this question difficult. It is meant to be difficult. It is the hardest question of this tutorial, definitely. But if you can, that means if you can understand this, then the rest is more or less something along these lines.
Just let me go die.
Huh? What? Is someone asking me something? I can't hear. Oh, you guessed square root 2 over 2 at first. Yeah, it's almost there. Well, yeah, but it's not over 2 I guess. You got this thing. Yeah. So so in you can't see my screen? How about now? Anyone else have the same problem as me? I mean, you can still cannot. Oh, it happens. It happens to, yeah, unshare and share again. So let me do it. How about now? Yeah, it happens. Yeah, it happens, right? So it never happened to me on Linux before. I wonder whether it is a Windows problem. Okay, now, yeah. Yeah, so I will upload the rest of the things in the Moodle, right? So you should have enough information to help you solve the other questions. Windows loud, yeah, correct. I agree. That's why I don't like to use Windows. I use Linux most of the time. Seems like I only go to Windows when I want to do things like this or when I want to play games, because most games are only on Windows. If the question doesn't mention if it's elastic, do you consider them as elastic? Generally speaking, no. So if it doesn't mention, right, then to be safe, do not treat it as elastic, because elastic is a special case, right? Kinetic energy conserve. So if it doesn't mention, right, then to be safe, do not use kinetic energy. Yeah, the computer COVID from Monday evolved. It went to Windows. Okay, so since I have finished talking my thing, I will stop recording. Shuhuang Wi-Fi really bad lah. Oh, yeah, that's fine. That's fine. Why the question KE is not conserved? Which one? Which one? Campus Wi-Fi. Oh. Oh, you mean this one, right? This question, the earlier one. Okay, so the KE here is not conserved, and it might be something I forgot to say in the class. So generally speaking, right, so this thing KE is not conserved, right? And here is an easy way to remember. So let me write it down. Okay, if the two objects stick together after collision, KE not conserved. So this is a simple way to remember. So that means it is inelastic. Okay, so no, because for this situation, right, I have M1, U1, and then I have M2, U2, and then after they collide, they just stick together, right, M1 and M2, and then they move at the same velocity v. So M1 U1 plus M2 U2 is equals to M1 plus U M2 final velocity. Okay, then the kinetic energy is not equal. Okay, so the final kinetic energy is M1 plus M2 v squared. So this is not equal. Okay. Oh, Jiahao is using VPN. Always no internet. So campus Wi-Fi is really bad, is it? Question 8. So Charles is asking this, right? This is question 8. These two stick together after collision. So remember this. Basically, kinetic energy will last during collision. Yeah. So well, again, this is too much detail, but like the bullet case, right? Like the bullet case, as it embeds into the thing, from here to here, there is friction because it's friction against the box. So that is why kinetic energy is not conserved. But for this case, right, even in the ideal case, there's no air friction and things like that. But if we know that they stick together after collision, right, why is it sticking together? So maybe there's a glue here. Okay, if there's a glue here, so there's a glue that it will make something to stick together, then you cannot assume it's elastic anymore. Basically saying, you know. Yeah, so no air friction. Even if there's no air friction, as long as they stick together, KE not conserved. Wei Zheng asks, what is V after but after V? Oh, yes. So after this, there's no more external force, no more other collision, no more momentum, then everything will be conserved here because nothing happened after that. For question 8, something happened, so the energy will conserve, right? So from here to here, after the collision, after this, the total energy, mechanical and potential, they will be conserved. So that's why you can use this equation. Okay. Okay, so yeah, does anyone have any more question? Anything else to ask? You may use half mv square. Yes, so to replace half I omega square, yes, you can. That means you need to know the omega. Yeah. So the v now after collision during swinging is the tangential speed. So you can use either one. For the spinning chair problem, if we spread our arms, there's no work done by our arms. Correct, yes, there's no work done by our arms. Yeah, because if you're spinning, right, you just need to relax your body. That means you're not exerting any force. So your arms no need to do anything. It's just like spreading out, and the reason is because of the spinning. So the spinning will contribute. The spinning is the centrifugal force that is spreading our arms. So we can think of it as the force coming from two places, right? Our muscles can contribute the force to spread or come in or go out, but the spinning will contribute a centrifugal force. So if you don't do anything with your arms, so your arms don't contribute any force, only the centrifugal force contributes. So yeah, that is why. Until your arm gets the max length, yeah. Here there's no concrete force in this case. Because you can say that the T in your arm. So then we go into more details again, like the tension in the arms, the distribution of force. The T in our arm will not is definitely not uniform, not constant, right? Different position will have different values of T. Yeah, so I would agree with Zuri. It's a complicated case, and I have sort of like covered our chapter almost, but I try to avoid mentioning centrifugal and centripetal together too much. So it is a complicated case. Yeah, you can say that, and the reason is kind of right if you think about it using the concept of centrifugal force. So yes, it is an advanced case, and the reason why I avoided mentioning centrifugal too much, right, is that the reason is because it's not a real force. So there's no actual force happening here, and the reason why that is as if it's a force is there's an accelerating frame. So it's a non-inertial frame. So if there's a non-inertial frame, then there is some it is a how to say a fake force, imaginary force. No, so so the reason why is because, right, we always remember Newton's law. Newton's law said that if there is no force, object will have constant velocity, right? So there's no force, object will have constant velocity. That means if there's no force, nothing will happen. At most there's no acceleration. But for things that in a spinning chair, we have circular motion. Circular motion, we have acceleration, right? The radial acceleration. So from there we conclude that, okay, if anything going in a radial acceleration, there must be some force that contributes the radial acceleration. So that is where the force comes from. So yeah, then but even though I say that, right, it doesn't sound like a satisfying answer, because okay, there's a radial acceleration, and then there must be some force that make it go in a circle, but what force is it? That is where Zero was saying is correct, is that it's very complicated, because if it's your arm going in a circle, right, then there's a tension along your arms. So if you pull your arms in, then there's a muscles that work against this. If you let go of your muscle, then the natural force is the tension along your arms to spread everything out to go in a circular motion. So it's like the direction, everything is too messy and complicated to solve. You can analyze them separately, but if you're talking about arms, right, then okay, fine, like arms in circular motion. So when you bend in your arms, what is the direction of your net force? That is also a bit hard to solve, and you can solve, I think, but yeah, it's gonna be complicated.
Sir,
Yeah.
yeah, I think like if you hold a rope, and down the rope, like there's a ring or a rock, that just something with mass,
Yeah.
and then you spin yourself, and like the rock is likely to go upward, or you can say go outside, I mean backward, with the center, and so why is it happening? I mean, is it just because lack of the centripetal force, or
Yeah, so we can
I
answer
mean,
that.
because the radius must be large enough, so the centripetal force will enough for it.
Yeah. So what you're saying is hold the rock at the rope, right?
Yes.
Then so okay, so if this the case, then this is the normal, the tension will give you the centripetal force, so that one is okay. Then okay, so let's say if we pull the rock in, so it comes to here, right?
Yes.
It comes to here. So that means during the pulling, the the so the tension will have to change. Okay,
Yeah.
because
So I'm trying to say is that it go out. It's just it naturally go out,
yes,
and so it's just basically it's just because of the motion that it's like spinning. So it's
right,
because of the motion, but not
right,
because of the force, right? Or
right. So if you
so,
so actually, there's two steps. So if you let go of the string, as it spins, it will
yes.
naturally go out
Yeah.
until it stops here. And the reason why it stops is it has a max length, so the tension,
Yes.
then the tension is the one that you will make it go.
But uh so is it that we can say the centripetal force is to um adapt the motion, that the radius.
Yes, yes.
Okay,
Yeah.
thanks.
Uh, so because what we do know, no matter what, what you say is right. No matter how complicated the force is, once we know it's a circular motion, then the net force is mv squared over r. That's true.
Okay.
So in example 6.4.1, why is the final angular velocity greater than initial? So kind of like what we were saying, right? You put is conservation of angular momentum, right? Where was it? 6.4.1. Yeah, this one, right? So there's no external torque, so angular momentum is conserved, and once you put in the numbers, you get this higher number, right? And so that is even just by considering angular momentum. So we can conclude this already even before we start talking about the work done to bring the dumbbell in and things like that. But basically, to conservation of angular momentum says that initial angular momentum must be equal to final angular momentum. So we got this equation, and that is how we get omega 2. And omega 2 is larger than the omega 1. Does that answer your question? I decrease. Yes. Yeah. So correct. Yeah. So what happens is I decrease. So this one is smaller, but to make this equation remains the same, omega must increase back to make sure this number is the same as this number. Yeah, true. The person just rotate by himself, kind of. Yeah. Can we say delta E is used to change I? Yeah, yeah. So like just now, is related lah. It's like because I change then E change, so they are interconnected. The person just rotate by itself. Yes. So that is why it's very interesting, right? But you must have some initial non-zero omega. So let's say you're initially spinning very slowly, right? Initially spinning very slowly, but without external influence, you just pull in the dumbbell, you end up spinning faster by yourself. And that is why how the ice skating, like people do this kind of thing, right? So when ice skating, you move, right? And then if you pull the hands close to your body, it looks like you're doing some pose, but kind of the reason why you have that pose, you end up spinning faster. And then you do a next pose, another ice skating pose, then you spin slower. So using this, you can change your angular momentum. Okay, so if you're, I don't know if I Google ice skating spin angular momentum, you can see some interesting videos. I want videos. Okay, so see, when her body all spread out, she's spinning, she's gonna pull her legs in, then she spin faster, right? Yeah, so that's angular momentum. What are you saying? What's input, what's output? Moment change with E or E change? I mean, they are not. They are two different things. So we don't really say what cause, who caused what. Because you have moment is the force basically. You exert a force to change your system. Yeah. So I think the simple way to say is the force. The force change moment of inertia, and it also change the energy of the system. Because force does work. And because the force will push the mass into the object, so force is pushing the mass. Like the force is pushing the mass in, so it changes the moments of inertia. Yeah, the moment of inertia is about the object itself, that's why. Let me stop the recording. This is running too long.